alters the background state of the California current. The other argument is for local forcing, and that is that there's a stationary of negative wind stress curl, positive wind stress curl, that tend to energize the standing meanders of the California current through an Ekman pumping response. And so it's really those two that we're going to be looking at. And dynamically, this wind stress curl balance is something like this. So if we say that relative vorticity is being controlled mostly by wind stress curl, and we linearize that, we get something that looks like this. If we say that we're looking specifically on the largest spatial scales, just through scale analysis, remove the two terms with space derivatives in them, and then differentiate further in x, we get a balance that looks like this. So this along-shore current V is largely the response to a cross-shelf derivative in the wind stress curl. So what we're looking at is really which of these two mechanisms dominates. So for this work, we use an ensemble of 3 Brahms hindcasts in the Northeast Pacific region. They go from 1950 to 2008. They have 10-kilometer resolution, which means they're eddy resolving, which is of course important. And they have 30 vertical levels. They're forced by NSEP reanalysis, which I'm sure we can get to in the questions. And 2 of them use a boundary condition derived from the global ocean model OPUS. And what this is a boundary condition that is nudged to time-dependent changes in OPUS. And it allows us to simulate the variance coming from these coastal track waves along the southern boundary. So we have 2 runs that include this boundary condition. They're called OBC1 and OBC2 for OPUS boundary condition, and one that doesn't include it as a control. So to get an idea of what this boundary condition actually means, we can compute correlations between medium 3.4 and anomalous sea surface height in the OPUS model, in our first Brahms run, OBC1, and in our third Brahms run, the one that does not include the boundary condition. You can see that in OPUS, we get this really strong correlation along the coast, indicating that this ENSO signal is propagating effectively along shore. In Brahms, we still see it, but it's a little bit attenuated, indicating that the boundary condition doesn't capture quite all of that variance. And then in the no OBC case, where there's no boundary condition, we don't really see much coastal track wave variance at all. It's really just this signal here that comes from the atmospheric teleconnection. So we do have some confidence that the OPUS boundary condition can accurately reproduce the coastal track wave dynamics that have been said to force the California current in the past. And if you're interested in more, I would point you to these 2 studies, which have used these integrations in previous climate studies. So this is the same data visualized in a little bit of a different way. This is from our OBC1 integration. Correlations between medium 3.4 and sea surface height on the left here, and correlation between medium 3.4 and V on the right. So we see that there's, just as we saw before, there's this really nice pattern of correlation offshore and sea surface height, whereas V, we get this really small coastal layer. If we lag that correlation forward in time, I have to keep your eye on both of these simultaneously, we see that 6 months, 12 months, 18 months, that ENSO signal propagates really effectively offshore as a Rossby wave, just as one would expect in theory, but only in sea surface height. It doesn't propagate at all in V. The small sort of coastal correlation you saw kind of goes away. So the conclusion we draw is that this ENSO signal is really only propagating offshore effectively in the sea surface height. It's not really doing much for the transports. So our next question is naturally, how effectively do Rossby wave signals propagate this way? So we have to exclude first all Rossby waves and mesoscale eddies and other things that aren't specifically what we're looking at. So we break our sea surface height field eta into 2 components, an eddy scale, which is less than 200 kilometers, and a large scale, which is greater than 200 kilometers. And we use a spatial smoother to isolate the large scale, and it's really this what we're looking at for large scale transport variability. So first what we do is we take this domain here and align it with origin such that the 0 here represents the coastline. And we compute the maximum correlation between coastal sea surface height and offshore sea surface height for lags of up to 3 years. So what this figure is showing you is that there's a really strong signal from the coast all the way out here at around 30 degrees north. Of course, it's a little bit less as you go further north. So there's this really robust offshore decaying correlation with sea surface height. If we look at the month at which that maximum correlation occurs, we see that we also get this really nice pattern where this where the time it takes is increasing linearly, and also we see this nice beta dispersion as you go further north. So this is really exactly as predicted by theory in terms of sea surface height propagating effectively offshore as a Rossby wave. If we make equivalent plots for V, we don't really see that. We see that the maximum correlation with the coast is very small, pretty much just offshore, and that the lag at which that maximum correlation occurs is at 0, indicating that any correlation is really just a feature of the spatial smoothing rather than any kind of effective Rossby wave propagation. So if Rossby waves don't characterize this along-shore transport variability well, what does? So next we'll look for a stationary pattern. This is the mean V from our OBC1 integration. And we take a profile, it's the same region of interest, looks like that. So we see that there's this nice positive area of return flow here, and then here is the core of the California current. You can take this area within these bounds and average it to form a time-dependent index. Gives you something that looks like this. So with the assumption that now it's a local wind pattern, rather than any kind of coastal track wave, Rossby wave sort of mechanism going on, we just compute a projection of this mean V index onto the wind field. Projection on the wind stress looks just like this. So we get this very nice pattern of gradient in the wind stress curl in the cross-shelf direction. If we compute an index of this pattern, we get something very noisy. It looks a lot like pretty much any other atmospheric index. But going back to that dynamical balance we talked about on extremely large spatial scales, where V is being driven largely by this gradient pattern, we can use this index to drive an AR1 model. We get a pattern that looks like that. And it actually correlates extremely well with that mean V index. So it's really this local wind stress curl gradient that tends to modulate large-scale V. Our next question, of course, is what is the significance of this gradient pattern? Because we kind of just fished it out with a projection. If we look at the first EOF of wind stress curl locally, we see that we get that same cross-shelf gradient. So the wind stress curl pattern represents the locally dominant mode of variability. This PC1 is correlated with that wind stress curl index at around 0.9. So it's really this first EOF specifically that we're talking about is controlling variability. It also has a strong resemblance to the mean. So that means that the wind stress curl gradient pattern modulates along-shore transport as the leading mode of variability and represents a strengthening and weakening of the mean. So we've got this nice little narrative about what exactly is going on with large-scale transports. Basically, the mean has some sort of modulation to it, and that tends to produce an Ekman pumping response, which gives you this large-scale transport variability. Okay. So we feel like we've done a pretty good job with large-scale transports. But the question is, how much of the overall transport variance have we actually explained? Which is another way of asking, on what spatial scales is variance concentrated? If you make maps of the standard deviation of sea surface height and V, you see that they're concentrated in about the same areas. And this uses the same normalized coordinate system we've been using in the past. Arrange everything close to the coast. If then you compute the standard deviation of just the large-scale component, so what we've been looking at previously, you see that sea surface height retains a lot of its variance, whereas V really doesn't. It's really on the eddy scale, we haven't looked at yet, that most of V's variance is concentrated. So until we can understand and quantify and determine the forcings of this mesoscale variability, we can't really say we fully understand California current system transports. So if you look at this map, which has just SST, a snapshot of SST anomalies off the coast of California, you can really see that it's being driven mostly by eddy transport. You don't really see many large-scale gradients in evidence there. And this was sort of the broader point of the study by Holmes et al., which used some of our same integrations. So what they did was they released a passive tracer around here, and monitored in what ways, by what means it was convected offshore. And you can see in the figure here that it's really through eddies, through mesoscale eddies, that it's being transported. A1, A2, and A3 all represent anticyclones. C1 and C2 represent cyclones. It's really there that this large amount of tracer is being concentrated. There aren't really any large-scale cross-shelf transports that are managed. So these deep anticyclones here are especially effective at moving tracers offshore. This figure here comes from Criterion et al., who use ROMS modeling, like we do, to look at California current system eddies. And this is a composite deep core anticyclone from across their entire configuration. And so you can see, its characteristic patterns. Deep core anticyclones tend to be associated with high SST anomalies, high sea surface height anomalies, and a vorticity maximum that's generally around 400 meters depth. So that's one species of eddy you generally find in the California current. The other is a surface core cyclone. So it's the opposite. It rotates cyclonically. It has negative SST anomaly and negative SSH anomaly. And its vorticity maximum tends to be located near the surface. So we saw before that both of these types of eddies, anticyclones and cyclones, were effective at transporting tracers offshore, but maybe not in the same way. It seemed like anticyclones were integrating more of them. They also may be forced by different methods. So when we're looking at the forcing methods of mesoscale eddies, we really want to consider cyclones and anticyclones separately. So that's, I will convince you that hopefully that we have done that effectively. So the first question is how well our model represents the California current system eddy field. This is RMS vorticity from MESO satellite observations, 1992-2009. And you can see that there's a robust area of eddy activity offshore the California current. And you can see the signature of their propagation to the west. Let's look at an equivalent map from our ROMS image. So there are definitely some biases, especially around the lower portion towards the southern boundary of our integration and around the Gulf of Alaska. There's also some steering going on that may not be entirely visible, but we do capture this large band of vorticity that is of primary interest. So how are we going to quantify mesoscale variability? So here it's done with vorticity, but we said we wanted an approach that would quantify anticyclones and cyclones specifically. So we tend to count eddies. That's what we do. So there is quite a bit of precedent for counting eddies. We have a slightly different procedure for doing it, but it does have its precedence. So the first thing we do is to develop monthly fields of the Okubo vice parameter W. And W is not a particularly complicated quantity. All it represents is the dominance of rotation over shearing and stretching. And in a non-divergent environment, it simplifies to this. So when this parameter is strongly negative, it represents an area of an eddy. So you can see these areas of light blue here all represent eddies, or at least potential eddies. So once we've got monthly fields of it, we choose a specific contour that we want to count. There's a lot of art to choosing a contour, and something I would love to talk about in questions. But suffice to say that we base the contour that we chose on previous observations and modeling studies. We want to get a count that's in accord with those. On visual inspection, so you want something that looks like an eddy to be counted as an eddy, and counts from continuous contouring schemes, where you use multiple contours and take the outermost one that fills all of the components. So once we've got a contour that we say is an eddy, like this one, we have one other test for it, which is something called a shape error criterion, where we decide that an eddy has to be sufficiently circular for it to be counted as an eddy. And in areas of the California current where you don't have a very strong background flow to kind of squeeze eddies to shape, it's a really good strategy. So the shape error is the variance of the contour from a circle that has the same average radius. So this one has a very small shape error. You can see it roughly conforms to that circle, so we include it in the count. A contour like this one doesn't really conform to the circle, so we include it. So that allows us to develop a count of eddies for each specific month. Other people do tracking, do things like that, but for us what's really important is a time index of eddy activity for both cyclones and anticyclones. So we divided our study area into a northern and a southern component. And the reason for that is that we found that a lot of that ENSO energy tends to be attenuated north of the Southern California bight. A lot of that coastal track wave energy has already radiated away as a Rossby wave or been lost to friction or other processes at that point. So our assumption going in is that the northern half is going to have less ENSO variance than the southern half. That was our logic in dividing it up. So to get not just a spatial view, but also a time-dependent view of how well we're reproducing these eddy records, we also counted contours of the VSO satellite, of sea surface height anomalies. That's actually done much the same way, except instead of counting contours of the Yokobo Weiss parameter, you count contours of sea surface height in a high-pass field. So we end up with something like this. So the red represents a composite of anticyclone counts from our 3 model runs, and the blue is anticyclone counts from AVISA. You see that not only have we captured the stationary statistics, but we've also got a lot of that interannual variability, which is very nice. It's difficult to determine significance with something this short, but 0.42 is actually quite significant in this case. Now, if we look at the same with cyclones, we really don't see that agreement. We do get the stationary statistics, but there is very little interannual signal to capture, and we definitely don't capture it. We get an R value of 0.08. But I think I can convince you that that's not, there may be an explanation. So if we take our model integrations and look over the entire model run, and we compute spectra, we end up with these. So you can see that anticyclones and cyclones both in the Northern California current have a very strong peak at a yearly frequency, indicating that they're both strongly seasonal. And there are different observations. You can get a lot of disagreement on how seasonal eddy activity is, especially counted eddies versus eddy kinetic energy. But we definitely saw a strong seasonal cycle. But what's of more interest to us is this band here of significant low frequencies. That's it's bounded between 0 and 0.3, so around periods around 3 years and longer. It's really that power that we assume has some sort of climate signal, some kind of interannual variability that we're interested in. So given that it's significant, our next question is it deterministic? Eddy formation is a chaotic process, and it's strongly intrinsically variable. But so our question is, how much of this is actually forced? So what we do is we low-pass to isolate just these significant frequencies and compute correlations of each of them with a model composite. Anticyclones are very strongly correlated, so we can say that around 25 to 35% of their variance is deterministic, is forced. Cyclones are not as well correlated. We're saying around 10 to 25% is deterministic. Since all 3 runs are forced by this NCEP reanalysis wins, that's why we can assume that there's a signal going throughout all. And you can definitely see it visually in anticyclones, that there is this very strong atmospheric signal that's going through. So our next question, of course, is are anticyclones and cyclones forced similarly? We made a big deal about separating them into different polarities, but is that really important? If we correlate a composite cyclone count and a composite anticyclone count, we find that they're very well correlated at 0.75, with anticyclones lagging behind around 8 points. So, since that represents pretty much all of the deterministic variance in these time series, we can say that they probably share a common source of forcing. There's probably one single or one set of physical mechanisms that force both of them on interannual timescales. So, what do we look for, and where do we look for? So these are spatial maps of eddy activity, anticyclones and cyclones, or they're composites from all 3 integrations for all times. And the way we make these is pretty easy. We just stick a normal distribution every place where we count an eddy at every month. These maps are specifically summer eddy activity, so this is where we see most eddies being formed. And you can see that anticyclones have this nice, robust offshore progression. Cyclones, not quite as much, but still some. But really, this is the area that we want to look for physical forces, this being the cradle of eddies where it's formed. So our first index that we developed in this area is a barotropic velocity index. It's barotropic in the sense that it is depth averaged. So all we do is we take a longshore velocity, depth average it up to 400 meters, because remember the vorticity maximum of a deep core anticyclone is usually there. And we develop an index of this longshore flow. We find that it correlates at around 0.5, so it does all right. The second index we developed is a baroclinic index. This one's a little bit more nuanced. So it's generally assumed that eddies are formed within the undercurrent, which travels below the California current. And the boundary between those is generally taken as isopickle 26.5. So what we did is we formed a finite differencing about isopickle 26.5 to compute an index mostly of isopickle strength. It's a measure of stratification and of potential baroclinic instability. And this index also correlates with the composite anticyclone count at around 0.5. When we looked at whether these two indices were secretly the same, if they had anything to do with each other, we actually found that they were largely orthogonal, completely uncorrelated for virtually all meaningful lags. So that means we can combine them into a single diagnostic model of eddy activity. So this red curve here contains both a component from this barotropic index and from this baroclinic index. And we find that it's a really good predictor of eddy activity, correlated at around 0.8. So we think that there is a component that is barotropic, which is from shearing. We think that there's a component that comes directly from stratification about the undercurrent. But given its success in capturing this variance, can we connect it to either local or basin scale forcing to get back to the major problem of the thesis? So if we just project it onto the wind once again, before, we get this same cross-shelf gradient of wind stress problem in our area of interest. We make an index of that gradient. Find that it correlates well with this diagnostic model at around 0.62. It also correlates with composite anticyclones and cyclone counts pretty darn well. So we can say that Northern California current eddy activity, just like large-scale transport, is primarily driven by modulation of the local wind stress curl gradient. So it's this wind stress curl gradient that is communicating variance to eddies along two separate pathways through this barotropic velocity component and this baroclinic component about the undercurrent. So, we've got large scale, we've got eddies in the Northern California current, and now we're going to look at eddies in the Southern California current. So here we assumed that there would be a good deal more ENSO variance, just given that it's closer to the source of coastal trapped waves. We found it was a lot more complicated than that. So if we compare a composite anticyclone count and a composite cyclone count is the same from ESO satellite observations, we find that we really can't capture much interannual variability. There's not much to capture, and we probably don't capture. So if we look at the spectra, there's a little bit of a hint as to why. So these spectra, unlike the last ones, just come from OBC1 and OBC2. So these spectra only include the runs that have the OFIS boundary condition. And so once again, you have this significant interannual and decadal variance on the low end. They don't have a sequence. If we compare it to a spectrum that's derived from the no OBC run, so without the coastal trapped wave variance, we don't see any significant low frequency variance at all. Without that ENSO signal, it resembles a red noise process. So going back, you would assume that this variance was directly derived from ENSO. But, in fact, it's not. The anticyclone counts from OBC1 and OBC2 are only weakly correlated at around 0.3. And only OBC1 correlates with helium 3.4, also at around 0.3. So there really isn't much driven variance in these eddy counts at all. And although there is some evidence of ENSO signal, it's definitely masked by a level of intrinsic variance. So our next question is, why are Southern California current eddy counts dominated by this intrinsic variance, as opposed to in the north? If you look at seasonal maps of position of eddies, in spring, summer, fall, and winter, we see that they really don't propagate offshore effectively at all. They stay put. And so this is our argument that eddies in the southern part of the California current are recirculated back into the mean flow. And this longer residence time means that they tend to have much stronger feedback effects than eddies in the north. And that's what gives you chaos and intrinsic variance and unpredictability. So now we have what we think of as a complete picture of California current interannual variability. The first step is this dominant mode of wind stress kernel variability, which represents an intensification of the stationary mean pattern. That wind pattern energizes the large-scale California current meanders through an Ekman pumping response and leads to stronger alongshore transports, which you can read all about in our paper in DSR2 coming this month. Then we have Northern California current eddies. So wind stress curl alters the background state of the Northern California current, driving the formation of eddies which then propagate offshore effectively. And then Southern California current eddies tend to be recirculated back towards the coast, leading to feedbacks, nonlinearity, and intrinsic variance. You can read about that in our other paper in DSR2 coming up this month. So there was a third possible method of California current transport that time didn't really permit going fully into. But if you look at maps of zonal velocity across the world ocean, you see these features of these banding of eastward and westward flow all across the ocean. And they're called striations. And they're only really apparent in the long-term mean. It's not something you can really look at the variance specifically of interannual. But there's been a lot of debate as to what actually causes them, what's responsible for them. If you look at the same fields of view within the California current, you see the same banding, but it tends to be advected by the background flow towards the equator. So the third part of my dissertation was about how these striations are formed, and we used a series of Brahms integrations with increasing simplicity to try to find what were the necessary conditions of striation formation. And what we found is that these California current meanders are actually attached to specific features along the coastline, and they provide these persistent sources of vorticity, which then migrate offshore as a beta clip. So it's been suggested that they're eddy tracks, but we found that they still form, in a non-eddy resolving environment. We felt we made a pretty convincing case that they were actually consequences of these persistent meanders. So that's the final part of our picture. The meanders serve as persistent sources of vorticity, which propagates offshore as a beta. This gives rise to striations. And you can read all about this in our GRL paper, which came out in February. All right, so I think I've laid out the case there. Let's open up for questions.
Okay, we'll take some questions from the general audience before we grill Andrew. Anyone?
I'm sorry? In what sense? Calibrated? Well, it's a full hindcast of the Northeast Pacific that starts from rest with a realistic background stratification. And then you spin it up with NCEP climatology, and then finally you hindcast it with NCEP reanalysis waves. And so I don't know a better question other than to say that it's initialized with these various, these various realistic forcings and things. But we have, I can point you to my thesis where we have a little bit more in terms of confirming, it actually does reproduce the mean California current.
I was wondering about your thoughts about what controls the separation between those two.
Well, what we found, so there's definitely an atmospheric component to it. there's a Gucci paper that just came out about small scale winds affecting striation magnitude and such. But what we found really affected the scale of striations was really the amount of detail in the bathymetry. That if you just have